Pictured below is the graph of a normal distribution, or more specifically, a standard normal distribution. One of the most commonly discussed continuous distributions. You may have also heard people refer to the bell curve. When we talk about that, we're talking about a normal distribution. The standard normal distribution in particular is abbreviated as a capital N, and then inside a set of parentheses, 0, 1. This refers to the fact that in a standard normal distribution, we have a mean of 0, which is the center of our distribution, and a standard deviation of 1. When we talk about the normal distribution, it's also a good idea to talk about the empirical rule, which tells us about some of the properties of a normal distribution. The empirical rule tells us that 95% of all data values in a normal distribution are within 2 standard deviations of the mean. So our mean is 0, x equals 0, the center of the distribution. What we're saying is that 2 standard deviations below to 2 standard deviations above the mean, that represents 95% of our data. 68% is within 1 standard deviation. And 99.7% is within 3 standard deviations of the mean. So those are just some of the characteristics of our standard or of our normal distribution. In addition, we can identify this as being a symmetric and unimodal distribution. By unimodal, we mean that it only has one peak and then it slopes down on each side versus having, say, another bump that popped up somewhere along the way. So the symmetric unimodal distribution that we refer to as the normal distribution can be used to calculate continuous probabilities. And what we want to do in example 2 is sketch some of the probability statements on the distribution to see how those would be calculated. In part A, we want to find the probability that x is less than or equal to 1. In order to determine that, we would find a boundary line where x is equal to 1, and then the probability would be the area between the normal distribution curve and the x-axis, less than that value of x equals 1. We can't calculate that probability by hand, or we could, but it would take a lot of pretty advanced mathematics, so we'll look at using technology to calculate these results for us. But we want to go ahead and continue to visualize how these probabilities look, so we have an idea of what we're calculating later on. In part B, we're asked to find the probability that x is less than 1. That's actually exactly the same probability, because again, whether we have a strict inequality statement like less than 1, or we have a less than or equal to statement, those pictures, those probabilities come out to be exactly the same. In part C, we're asked to calculate the probability that x is greater than or equal to -2. So in this case, we would find that boundary line at x equals -2, and then we would be calculating the probability by finding the area under the curve to the right of x equals -2. In part D, we want to find the probability that x is bounded between negative 1.5 and positive 2. So we would find those two boundary lines and assume I actually hit that 2 there. Then we would calculate the probability under the curve bounded between those two lines. And for part E, we would be looking to find the probability that x is less than or equal to negative 1 or greater than or equal to positive 1. So we would again set up a pair of boundary lines, but in this case, rather than looking at the area in between, we'd be looking at the area to the left of x equals negative 1 and the area to the right of x equals positive 1. So in each of these examples, calculating the area of those shaded regions, which we'll do with technology, would give us those corresponding probabilities.